Hey everyone, welcome back to the channel. A few videos ago, we built a neural network from scratch in C++ to solve the XOR problem. If you haven't seen that one yet, I highly recommend checking it out to understand the math and logic behind everything. Today, we're gonna build that exact same neural network, but this time in Python using TensorFlow and Keras. And in this video, I want to show you how easy it is to build a neural network when you are using a powerful platform and high-level libraries. You'll see that with just a few lines of code, we can create, train, and evaluate a fully working model. So let's bring this neural network to life in Python. Let's start by importing the libraries we'll need. We'll use TensorFlow and Keras to build and train our neural network. So here we say import TensorFlow as TF, and from TensorFlow we import Keras, and from TensorFlow.Keras we import layers, and we need NumPy to work with numerical data, so import NumPy as NP, and matplotlib to visualize how the training loss evolves over time. So import matplotlib.pyplot as PLT. These libraries make the entire process much more streamlined. Next, we're going to define our training data for the XOR function. We'll create an array with all four possible input combinations. X, capital X, equals np.array, and here 0 and 0, 0 and 1, 1 and 0, and 1 and 1. Then we have data type. dtype equals np.float32. Then we create another array with the expected output. Y equals np.array 0, 1, 1, and 0. And dtype equals np.float32. Now it's time to define our neural network model. We'll use Keras' sequential API, which lets us stack layers one after another. So here I'm gonna say model equals keras.sequential. Inside parentheses, we have the list of layers. Our input layer expects two values, just like our XOR inputs. Layers.input, and we pass it shape equals inside parentheses 2, comma, and here we have another comma. Then we add a hidden layer with 3 neurons and ReLU as the activation function, which helps the network learn nonlinear patterns. Layers.dense, and we pass it 3, comma, activation equals ReLU or ReLU. Finally, we add an output layer with 1 neuron and a sigmoid activation, since we're solving a binary classification problem. So layers.dense, and we pass it 1, comma, activation equals sigmoid. Before training, we'll compile the model. This is where we define how the network learns. And here we say model.compile, and we pass it optimizer equals keras.optimizers.sgd. we use Stochastic Gradient Descent as the optimizer, and we pass it the learning rate. Learning_rate equals 0.05. For the last function, we'll go with mean squared error, which works fine for this small binary classification task, especially since it's what we used in the C++ version. But you can also try binary cross entropy for potentially faster convergence. So loss equals mean_squared_error Now let's take a quick look at its architecture using model.summary and run. Here, Keras tells us that we're working with a sequential model, meaning the layers are stacked one after another in a straight line from input to output. In the first column, layer type, Keras lists each layer in our model and its type, like dense for fully connected layers. The second column, output shape, shows the shape of the output from each layer. For example, non-3 means each input sample will produce a vector of 3 values from that layer, and none just stands for the batch size, which can vary. The last column, param, showed the number of parameters in each layer, which includes the weights and biases. These are the values the model learns during training. For example, in the first dense layer, we have 3 neurons. Each neuron has 2 input weights, 1 for each input feature. So that's 3 times 2, 6 weights. Each neuron has also 1 bias, so that's 3 more parameters. In total, this layer has 6 plus 3, 9 trainable parameters. You might be wondering why the table only shows 2 layers, even though we defined an input layer. That's because in Keras, the input layer doesn't actually count as a layer with parameters. It just defines the shape of data coming in. The first real trainable layer is our dense layer with 3 neurons, and that's what shows up first in the table. At the bottom we see non-trainable params 0. That just means all the parameters in our model can be updated during training. We don't have any frozen layers or fixed weights in this network. Now we'll train the model using the fit function. We're storing the result of the training in a variable called history. This gives us access to useful information like how the loss changed during each epoch, which we can later use to plot and visualize the learning process. And here's the code. History equals model.fit, and we pass it x, y, epochs equals 5000, and batch underscore size equals 1, and verbose equals 0. We run the training process for 5000 times, 5000 epochs. And the batch size is set to 1, meaning the model will update weights and biases after every single training example. And in Keras, verbose controls how much information the training process displays in the terminal. You can set it to 1 or 2, but I want to keep the training process quiet. In the C++ version, we used 3000 epochs to train the model, and that was enough to get the descent results. However, in Python with TensorFlow and Keras, we need a bit more training time. That's why we set it to 5000. Once training is done, let's use our model to make predictions on the XOR inputs. We'll print the raw output values first, then round them to see if the network correctly classifies the XOR function. And here we say predictions equals model.predict, and we pass it x. Then we print the predictions, print predictions, and then we say print predictions inside parentheses, rounded, colon, and we print np.round, and we pass it predictions. Okay, let's see the outputs. Here we can see the raw predictions, values close to 0 and 1, which represent the model's confidence. After rounding, we get the final binary outputs, which correctly matches the XOR function. So our neural network learned it successfully. Let's also test the model with new input, something close to 0 and 1, just to see how well it generalizes beyond the exact training points. So here we say test_points equals np.array, and here we pass it square brackets, 0.1, 0.9, and the data type is np.float 32. Then we say predictions equals model.predict, and we pass in test underscore points. Now let's print predictions. Print predictions. And just like before, we say print predictions inside parentheses, rounded, colon. And finally, we print the rounded predictions. Print np.round and predictions. Okay, let's run it. As you can see, the model isn't just memorizing, it's actually generalizing the patterns. Finally, let's visualize the training loss to see how the model improved over time. This will help us understand if the model was learning and converging toward the solution. We use matplotlib, plt.plot, and we pass it history.history, square brackets, loss. Then we give it a title, plt.title, and here's the title, training loss over epochs. And then we say plt.xlabel, epoch, and plt.ylabel, loss, which is MSE. And then we say plt.greet, true, and plt.show. As we can see, the error decreases over time, which indicates that our model is learning and improving. The loss is getting smaller with each epoch, showing that the network is gradually making more accurate predictions as it trains. And that's it. We have just built a simple neural network in Python using TensorFlow and Keras to solve the XOR function, just we did in C++, but in a lot fewer lines of code. If you found this helpful, don't forget to like, subscribe, and check out the C++ version if you haven't already. See you in the next video.